showing.
Slightly, he's okay with manual slightly.
वो just test करेंगे.
All right. Good afternoon, everyone. Welcome to the this week's colloquium. Our speaker today is Professor Arun Yethiraj from University of Wisconsin-Madison. As you know, he has been here for last couple of months. Yeah, he's been visiting us. So he is giving a very exciting talk about machine learning phase transitions. Now, to introduce Arun formally, let me call upon Ravi Venkatramani, and then we'll get going. Do I have to use this?
Okay. Yeah. Thanks, Manoj. It's a pleasure to introduce Arun. Arun is from the Department of Chemistry from the University of Wisconsin-Madison. Arun's expertise is essentially looking at stat mech of complex fluids. This includes polymer melts, surfactants, ionic liquids, and such. So Arun actually started out here in Bombay. I mean, he actually had his schooling here, and then he got his BTech in chemical engineering from IIT Bombay. And then following that, he went to the US where he got a master's from Louisiana State University. Following that, he went to NCSU for his PhD. There, he was working with Carroll Hall, where he looked at the theory of polymer melts and colloids, actually surfactants. Then he joined Ken Schweizer at the University of Illinois at Urbana-Champaign, where he was involved in developing coarse-grained models. And essentially, that's where he's also made quite a bit of a name for himself. He joined University of Wisconsin-Madison in 1993. And since then, he's been working on his research field. So his research is fairly well known in terms of providing great insights on essentially how fluid-like behavior arises. Essentially, looking at the stat mech of fluids. Essentially, he was honored with this ACS Physical Chemistry Division Award in 2022, the Theoretical Chemistry Award, and recently he's a recipient of Fulbright Nehru Fellowship. And I'm glad because he actually used the fellowship to actually come here, and he's been spending his sabbatical for the last few months here at TIFR. Actually, he'll be here till December. So if you want to talk to him and essentially just have a fun discussion, basically, then Arun is here till December actually. Right. Okay. Without any further ado, welcome Arun to give his talk.
Right. Thank you. Thanks. It's a pleasure to be here. So as he mentioned, this Bombay is my hometown, and it used to be Bombay when I left. They changed the name afterwards. But uh, and so it's been great hanging out here because I spent a few years of my childhood not far from here, actually, near the Colaba post office. And so I know the area, and it's been pleasant. And it's really been pleasant to be at TFR. A lot of people to talk to, and it's been a nice environment. Everybody seems so happy here. You know, I guess you don't read the news. Okay. So it's I've had a good time, and we'll be here for another month, and looking forward to this. So today I'm going to talk about machine learning of phase transitions. I should preface this by saying that I'm not an expert in machine learning. I don't know that much about it. I do know something about phase transitions, though. But so it's always a little bit nervous to talk about something that you didn't invent. But uh, I did give this talk at, not this talk, but a different version of it at the APS meeting, and all the physicists were so mad. And maybe some of you will get mad too, because the whole point of this is that there are many systems in nature or in our labs where there isn't a thermodynamic signature of a phase transition. Okay, so here is an example of liquid-liquid phase separation in cells, and they see these little droplets form inside the cell, which they call a phase. And they say it's a liquid-liquid because the droplet is a liquid and the cytoplasm is also a liquid. And there's no, in the experiment, there's no thermodynamic signature of this. Okay, it's sort of a structural signature. Another example is in polymer coacervates. Now, this is the simplest form. You mix a polyanion and a polycation, and you make, two-phase system with a supernatant dilute phase and a dense phase. But you can also have other sorts of structures formed. So here is an example of the same coacervates, but you can have a diblock where the positive is tied to a homopolymer of a different kind, and you have a negative part that's tied to it. So this diblock can make all sorts of different micelles as they reorganize, in order to satisfy hydrophilicity facing the water and hydrophobicity inside. But they can make all sorts of different structures. And in these systems in particular, there is a real question as to whether thermodynamics is important. Okay, so where I'm going with this is that you can think of a phase, and this is what gets people mad, by the way, without thinking about the thermodynamics. Okay, by just thinking about the structural signatures of the phase. Okay, so what got me interested in this many years ago, and I'll talk more about this next week, okay, in the other seminar, is ionic liquids. And this is a system where, this sodium chloride at room temperature, this ionic liquid BMBF NTF2, so TFSI. So this is a liquid at room temperature. There's no solvent. It's a liquid of these two ions, and it's immiscible with both water and with organic solvents. And this is a system which was interesting because it showed the promise of mixing it with different kinds of polymers and then creating a phase such as this gyroid, where the ionic liquid was in the channels and the polymer is outside. So these ionic liquids are very dense. They're very hard to get into a membrane. But if you could mix them with the polymer and then phase separate the polymer, this would allow you to create a membrane with the ionic liquid inside. Okay, so that was the goal.
What do you mean by this phase transition launch when you thermodynamics natures, meaning the pressure, temperature, and stability?
Right. So when you say thermodynamic, what do you expect? If you have a two phases in thermodynamic equilibrium, what do you expect?
If you cross it, one basically
What is equal between the two phases?
No, but if the densities are different, then it's already a thermodynamic difference, no?
Okay, so there is a thermodynamic difference in density, but usually you want, if you're looking at two different phases, you want what to be equal? Chemical potential, temperature, and pressure, right? So that would be your thermodynamic signature of a phase transition. But can you have a different sort of structure where you don't care about the chemical potentials being the same? Let me give you another example. So you take any of those systems, you heat them up and you cool them back down, you'll get a different phase. So is that an equilibrium phase? Is the thermodynamics the same? Right? So that's what I mean by thermodynamic signature, where if you were completely in thermodynamic equilibrium, then you would see the same thing every time. And can we study things which don't satisfy that? Okay, so that's, and a lot of these systems are like that. It's including the LLPS system. So they're history dependent. Okay, so the phase. A long time ago, I don't know if you know Jacob Israel-Ashvili. So he was giving a talk on different phases, and I said, "Is that a phase?" In the Ehrenfest sense. I was younger then, and I was really into all this stat physics, and Ehrenfest criteria. And he goes, "Of course, it's a phase. I see it in my lab. What do you want?" So, so I shut up, of course, but that was it. It's there, it's there. I study it, so it's a phase, and you can give it another name, but that's just semantics. Okay, so I'm on his team now, although he unfortunately is no longer with us. Okay, so yeah.
One something identify another one. The property will be very much similar. So
if you take one, worry. If you take one, sorry.
The system will prepare once, and then you bring it up and put it down. If they both belong to the same phase, is that many of the properties will be similar. It will depend on how you prepare.
No, all the properties will be identical. So
Okay.
yeah, that doesn't happen in many of these systems.
And even if it doesn't happen, you would call this a thermodynamic phase.
I will call it a phase.
Okay.
So he's going through a phase. Okay, so okay, so I mean, but when I approached this, I was only thinking about a thermodynamic phase. Okay, I was only thinking about a thermodynamic driving force for these phases to form. And what they did was they did this experiment where they looked at this ionic liquid, BMM-BF4, or actually EMIM, with only 2, not 4 of these. And they looked at this polymer PEO inside, and it forms an LCST. So this system will phase separate when you heat it, not when you cool it. So normally, when you have, say, benzene, cyclohexane, or something, phase separates when you cool it. That's called an upper critical solution temperature. This shows a LCST, so you expect that as you decrease the temperature, there is an entropy change that is negative. So this is something that as you increase the temperature, the entropy is going to be dominant because your free energy is G is H minus Ts. So as you make the temperature higher, Ts plays a bigger role. And that's why things are mixed, because the entropy of mixing favors mixing. But in this case, the entropy of mixing must favor phase separation. Okay? And so why is that? It's actually very common in polymers, but it's not well understood. And so this ionic liquid seemed to be a system where we could sort of study this LCST in addition to thinking about why there are some really strange things, why this critical density is at such a high concentration. There's some strange things about this system, which I will touch on next week, but not dwell on today. Okay, so also by putting in just one little CH3 group on here, the phase boundary changed dramatically, okay? And so I thought this was really kind of an interesting thing to try and look at. Okay, so why theory? So I was told this is going to be a general audience, right? And I've always believed that no talk can be too simple. Because if you give a really simple talk, people just think they're really smart. But if you give a complicated talk, they get mad because you made them feel stupid, right? So yeah, this is for the students in the audience, is never be afraid to give a talk that's too simple. Okay, it always works. Okay, for at least for me. So what we want to do is, develop molecular models for the real system. Okay, so these models can be very simple, but by solving for the properties of these models, we can, for example, change specific interactions in these models. We can get insight. So what we want is insight, and we'll get that insight by relating these properties to macroscopic observables. And the whole idea is to understand why this happens. Okay, so this is a slide I picked from the introductory talk I gave to grad students. We're not really interested in what happens, because the easier way to do that would be to do an experiment. I mean, experiments are generally easier than theory, right? So yes. That's true. Okay, so once we have the model, we're going to do computer simulation to get the phase. So that's our goal. And to get the phase boundary from computer simulations, which is what we want to do here for that system, that complicated system, it's really hard. Okay? And it's really hard because you want to simulate two phases that are at the same chemical potential. When you think about chemical potential, or maybe you don't think about it, but if you do think about chemical potential, what do you think of? What is chemical potential? So this is how I think about it. So to me, chemical potential is how hard is it to insert a molecule into the liquid. Okay. So it is dF/dN, so the change in free energy due to the change in the number of molecules. But essentially it's actually e to the minus beta phi, where phi is the work, the potential energy that you need to put it in. So the harder it is to put something in, the higher the chemical potential. Okay. So if you want two things to be at the same chemical potential, you have to take a molecule from here and stick it in there, and one from there and stick it in here. This is going to be part of your simulation. So when you're doing a Monte Carlo simulation, you move the particles around, and that keeps the temperature fixed. You can change the volume to keep the pressure fixed. But if you want to keep the chemical potential fixed, you have to do this particle interchange. And if you have a dense system, it is very hard. Okay, so that's where we were stuck. We tried a lot of different things, a lot of different ways of trying to insert molecules for more than a year, and didn't get anywhere until my student said, why don't we use machine learning? And I was like, what? So here's another, by the way, this is the example of the system that this actually worked from Mahesh Mahantapa's group and myself. And these are surfactants. And they make what are called these sigma phases and A15 phases. This is low symmetry packings. Okay, so they don't make like simple cubic, they make these complicated packings. And this is what the X-ray looked like. It's really cool. Okay, so you see all these different peaks. But this is one of those systems where it depends on the history sometimes. Okay, so if you change the water content in a different way, you get a different phase. But note that all these lines are drawn from looking at the X-ray pattern. So there's no sort of transition between these two phases as you go. Okay, so this is one of the things that got me thinking that you could use just structure for. Well, for example, dye blocks, right? Changing that coordinate changes the chemistry. So you can't just continuously go from one to the other. Right? Okay. So Someone asked me if I'd give a talk on machine learning, here when I first came, and I said, I don't know anything about machine learning, but here it is. Okay. So, so this is just a general overview of machine learning methods that I'm going to give here for a bit as applied to our systems. There are two kinds, supervised methods and unsupervised methods. Almost all the AI you see, in practice is supervised, almost all of it. And the way supervised methods work is that you take a system or many systems and you get a lot of data. And then you train your supervised model on that data. And then you use that to predict what would happen for another set of data. So, for example, a very common way of science in this field is to take a bunch of data, use some fraction, like say a third of it or half of it, to fit your model, and then see if your model predicts the properties of the other half. Okay. And if it does, you go, yes, I succeeded, give me a brownie for that. Okay, so it just shows that the model works on that data. But so I was talking to one of my computer science colleagues and I said, I didn't actually learn anything about the data from that, So what do you do in computer science? And he goes, we do the same thing. It's a way of testing if your model works on the data, but it doesn't teach us about the physics of the data itself. Okay, so that's a problem with supervised methods. Unsupervised methods, on the other hand, do not require training on your data. At least you're not using the same output from the data that you trained the system on. Okay, so there are two things. One is this input. This is the feature vector. For example, if you're trying to see what cars people buy, you might think of some features. Obviously the most important thing in the car is the color, right? So the color would be a feature, the horsepower might be another feature, and so on. And then this is your input, and your output was, the sales, and then you fit it, and then you do this for all the cars that you make in India. Oh, that wouldn't give you much data. Okay, say all the cars you make in Korea, and then see if you can apply it to some other model somewhere else. Okay, so that's the feature, and then you need some kind of output that would be sales in that case. In our case, it would be what phase do you have? Okay, so let me introduce you to this model, the Ising model. I'll talk about this quite a bit. It has spins that can be up or down. As you decrease the temperature, it goes through a magnetization transition. So it spontaneously magnetizes because two spins that are next to each other, nearest neighbors, but the same sign, have a negative energy. So the energy is minimized if they're all in the same direction. Entropy is, of course, maximized if it's randomly distributed. So that's what causes the phase transition. Here's an example of three different cases where your output can be, you have two here. So if the magnetization is 0, it's mixed. And if it is not 0, it is unmixed. So I can try to train a supervised model out here where it's phase separated, and here where it's mixed, and that would give me the 2 points to look at. Okay, so these supervised methods are a classification problem. You're training it on known data, and you want to test it on unknown data. And one of the things you have to be careful about is what your training data is. And the point I want to make here is that, okay, so if you have, say, a neural net, you have some input, you have these what are called hidden layers. They're completely connected in this case. So there's a weight that each of these lines carries. So you multiply this value by that, and then you multiply the value here, and so on. So this input transfers to 2, in this case, output, which we're going to declare to be mixed or phase separated. I'll talk more about the input feature in a bit. You can have other activation functions, more complicated forms. You can also use what's called a support vector machine. Now, this is for 2 variables, but in our general case, we're going to have many variables. But so if you know these two variables and you know what class they belong to, you can classify it by finding a plane. In this case, it's a line. If it's a three-dimensional system, it would be a plane. If it was, 3n, where n is Avogadro's number of dimensions, then it would be that many -1 surface that would divide these two classes. And then if something else comes up, you know the surface, and then you find which side of the surface it is, and that tells you which face it is. Okay, so you train it on this. So I want to emphasize that the training set is crucial. Okay, and for example, let's say I had this picture. Okay, it's of somebody you might know. Okay, so and I have this data set. It's in a website called Kaggle. So it's a repository of trained images. They have thousands of objects, millions of data sets, and they trained their neural net on these. And you can give it a new image, and it will tell you what it thinks it is. Okay. Now, if you go blindly without thinking about what your training data set was, then it tells you that this is a dumbbell. Okay. Then you could look at these people, okay, all of whom are here today. And this, it told me they were all tenches, and I didn't know what a tench was. So I had to look up a tench, and a tench is that. Okay. Then I looked up her, and you're never going to guess, okay, because it's so random. She is a television, okay, and she's wool, and this actually is the same person taken at. No, it is same person, different time. Okay, so and and he's a lab coat. Okay. So if this does have pictures of the database, also has pictures of people, but it's this is what was the closest representation to that. Okay, so there's actually a real problem with people. I'll get to that in a minute. But so okay, then I said, okay, let's not. That's too general. Let's classify them into cats or dogs. Okay, so this would be a simpler way of is this person a cat or a dog? And so, well, he's a cat no matter which way you look at it. So those are cats. These people are dogs. Of course, I used to be a dog, but I became a cat. And she used to be a cat and became a dog. Okay, so so now this I decreased the classification by restricting my training set to only cats or dogs. But if you didn't, I mean, this is obvious and it's funny because these are all actually people. But if you didn't know, if you just had a data set of numbers of positions or something like that, you wouldn't know if you didn't train it on the same system. So if you trained it on, say, a coarse grain model, and then you tried to query an atomistic model, you have to be a little careful of what the training data set is. So I tried to then think, maybe I can ask it to classify them as male or female, and not to give it in a talk, but just for my own, see if it can get that. And you can't do it. It won't do it for you. Because there are all these problems with gender. A binary classification of gender is basically completely off limits. So you can download data. They have lots of data of men and women that have been identified as men and women, but you have to do all that machine learning or AI yourself. And I did say I don't know anything about that, right? So I couldn't do that. So I didn't do that. And then I was thinking it would be a really bad idea to do it anyway. At least I couldn't talk about it. Okay, so so that's the thing. So what we did was the Ising model. So this is much simpler. So we trained it both at the very low and the very high temperatures. And then we looked at configurations in between. And then because the neural net has been trained, so basically what it gives you is a bunch of parameters. Okay, So if it is a 1, there are all these parameters related to those, those weights and the links. And so then if you have a new configuration, you feed it, and it'll be either a 1 or a 0. And so if you have an ensemble of configurations, then each one will be either 1 or 0, and then the ensemble will give you some number between 1 and 0. And if that number is greater than 0.5, so that is what I call the decision boundary, then you say it is one phase, and if it's less than 0.5, you say it's the other. And so this gives you, they've been colored by what that phase boundary is. So this is mixed, and this is mixed, and that is phase separated. So this allows you to then predict what the phase boundary is. So this is a different method. This is the unsupervised method. We're still using for the input feature just the raw spins, okay, just all the spins in a big vector. And then there are many temperatures. So, if you had, in this case, let's say you had 64 spins, that's 64 vectors. Then let's say you took 1,000 configuration, that's 64,000. And you did, 40 temperatures. So you can that multiplication all by yourself. And then what you need to do is to take matrix of that thing square and diagonalize it to get these things. So these are all very simple ideas. They were all done by Turing pretty much, but it wasn't until NVDA that it became really possible to do it on a regular basis. Okay, because now you can do these huge calculations in seconds. Okay, which you could do.
Feature space here.
All the spins. This is the Ising model. So so this is just all the features, this is the spins. And then I didn't say what the PCA was. Okay, so the features, let's call it X, right? And so it doesn't give you any insight to know what the principal components are, because you make the matrix X transpose X, right? And then you get the top 2 eigenvalues. And those are your principal components. So it doesn't give you any physical sort of insight on that. But does it work? And yes, it does. So and this was a big surprise, So here's the prediction. The Ising value is 2.29. So this is really close to the actual value, and very accurate for this 2-dimensional Ising model. So this is the PCA, and then here are system sizes, different system sizes, and we get the same critical point pretty much for all system sizes. So one of the things in critical phenomena is that there's a huge system size dependence. Okay, so it's sort of like this. When you have a critical system, there's a correlation length, and this thing diverges at the critical point. So as soon as your system, the correlation length equals the box length, as far as your simulation system thinks, it is infinite, because the box length is the biggest length scale in your system. So the smaller the system, the sooner it will face it'll become critical, right? So your larger system will have a lower critical temperature, smaller system will have a higher critical temperature. Finite size scaling tells you what this should be. It goes as L to the minus 1 over nu, where nu is 0.693, is a universal exponent. So this doesn't, first of all, it doesn't have that. Secondly, there is nothing in this model that has any information about the critical point, because it was trained for the mixed and phase separated states. So there is nothing in this machine learning model that tells you that there is a critical point. Okay? So why it works is a bit of a mystery. Okay. So we wanted to do it for off-lattice systems. So there's so we're using the same CNN, convolutional neural net, that was used for that dog-cat thing that I showed earlier, okay? And which was clearly so accurate, right? But so you take our simulation box, let's say you have red spheres and blue spheres, you sort of grid it. So you put it on a grid, and then you take what's called a filter. So you take this filter through, let's say your red is 1 and your blue is -1. And this filter is some size. We optimize the size, but it could be 2 by 2. So you go through your whole system, and then you take the average spin that box. Okay, so that's get some correlations of neighbors and all that. So that gives you this convolution layer, and then you flatten it into a single vector, and then you apply your neural net. This is a supervised system, and you get this phase boundary. The training set we use is mixed or phase separated. I actually didn't like this approach that much at the time, and now I don't like it at all. But there are other better approaches. But it cares which direction your box is in. So if it is, if you rotate the box, you get a different CNN out of it. So in fact, I didn't do this, but if you take those dogs and cats and rotate them, you might get a different prediction accuracy. Also, if you took a dog that was, thrown in the air, someone told me about this, I don't know if it's true, and took a picture, and then it didn't recognize it as accurately as if it was just sitting, because it had never been trained on things that were thrown in the air. Okay, so, so what you get out of this is this probability, that it is mixed. And so from that, you can get the phase diagram. And the phase diagram, I will show in a bit. So these are our model systems. I already talked about the Ising model, then the Leonard-Jones liquid vapor, and then this binary symmetric polymer blend. But if you look at this phase diagram for that, the Widom-Rollinson, I'll talk about this a bit. So it's a really kind of simple system with two very famous names, right? Widom and Rollinson, my God. So it's a very simple system, that binary mixture where AA and BB have no interaction at all, and AB is just a hard sphere. And so the independent variable is not the temperature, it's the density. When you increase the density, this thing starts to phase separate like crazy. And so at high densities, it phase separates. It's completely symmetric. And this is just a binary blend where Leonard-Jones blend, where this cross interaction is smaller than those between the like. And so this thing has a tendency to phase separate also. So these are our model systems. So let me just look at what this predicts. So we are still in a phase where we can't actually have people believe that the ML works. So far, we always have to also do it some other way. With the simulations that I said were difficult, to convince people that, when we did this, we weren't convinced ourselves, but to convince people that it's giving the right phase diagram. Okay, so here we're comparing our red supervised one to previous results from other groups. Okay, and here. Now, for this case, we had to cheat a little bit. Okay, so when you're evaluating this, when you're training it, you have two equilibrium phases, right? Somehow you got a phase separated system and a mixed system, and you trained it on that. Yeah.
But what is making them equilibrium state?
Entropy.
So in one case, the entropy, so the attraction has won that entropy, so that's why, or the interaction has won it, so that's why they're two different. So in what makes them like that? That's again a question, because you're keeping them in different orientation. That's what I understood.
Oh, that one. So let me just go back to that.
You make it mixed state, and what orientation make them into different?
So these are all mixed, and these are all phase separated.
Yeah.
Right? So the mixed one is mixed no matter what the orientation. But as far as the CNN goes, it's a different configuration. That convoluted method, the convolution method, if you rotate something, it has a different feature. So, right. So then you have to average over all orientations.
Because it's like at least a binary system, because like we take 20 amino acids and then we see the phase separation terms. Trying to link everything somehow to understand it in more detail about it.
So the mixed state is at high temperatures when entropy is important, right? At low temperatures, the entropy is less important because it's multiplied by T, right? So delta G is delta H minus T delta S. So that when T becomes small, then your free energy is equal or more, your energy or enthalpy is more important. So that wants this thing to be phase separated because the interactions are such that they will phase separate.
Just for anything. In case of aluminum, we call it as a homopolymer or heteropolymer, where like it's a electrostatic ribbon or phi or cation pi methyl pi, something like that. So that is what I was trying to basically when you say two spin, so it's
So
like plus minus. So when something is going like maybe on the plus at one side and on the minus at one side, that's clear.
So you want to think of this in terms of dispersion interactions. So what is driving this? In biology, you have, cation pi is one of them. There are others, electrostatics, but there is always also dispersion interactions, van der Waals interactions, short range attractions, right? So you can always have a liquid vapor because of these short range interactions. And in this case, you have two liquid phases because the attractions between the unlike species are weaker than those between the like species. Right? So that's what makes them phase separate when you cool them. But when you heat them, this attraction is overcome by the entropy you gain by mixing it.
Small, and then we can have it.
Right? So at high temperatures, you think entropy and it'll always mix. Did you have a question? For which one? So this is just the chi-square difference. Yeah, let's talk about that later. Okay, that's a.
Sorry, just one clarification. This rotation problem, I mean, is it because of this when you flatten and when you actually create a vector, there is some loss of information there?
Right, because you're going sequentially. So if you go sequentially in one side, if you rotate it and you go sequentially in the same order, then you have a different sequence of numbers, right?
Yeah.
That's why.
Right. So there is some, because in the sense it should be completely invariant. I mean,
It should be invariant.
There is
You could use a different feature. You could use, say, the distance between particles. Then that wouldn't have this problem. Okay, so what happens here is that when you're evaluating the system, you're always out of equilibrium, right? So if I start doing simulations here, then all the simulations I do under this boundary here, all of them are out of equilibrium, right? So if I did them long enough, they would give me these two separate phases. But I'm saying that's okay because I have these non-equilibrium structures, but they're, I'm just going to use this method to distinguish between the mixed one and when these out of equilibrium phases are somehow different. But what happens in this case is that, and this happens in many mixtures, is that these states can have different structures. For example, in this, if I looked at a phase separated system here, this would be lamellar because the two phases would be separate. But in here, I can get all sorts of, network phases and other complicated things. And since this model was only trained on the lamellar and the mixed state, it gets confused. Okay? So you have to retrain it as you change the temperature. So that was the little cheating we did. Okay. So we wanted to get away from that. First of all, I wanted to get away from the supervised methods. Then I wanted to get away from that CNN because of this rotation problem. And it was also too intensive. It was like for each configuration, we had to get this entire vector, and then we had to generate many configurations. And we thought, is there a better way where we can just use a single number for each particle, like in the spins, and then use that instead of having to go through this entire structure? Okay, so we came up with this thing called an affinity, where we take this particle and we go out a distance r cut. And if there are more of A than B, then it is +1. And if there are more B than A, or if they're equal, then it's -1. Okay, so this sort of replaces for each particle, it gives it a spin. Okay, and it is now it's invariant because this is just a number. It doesn't depend on the position of the particle. Okay, and then there's one parameter, and this turns out to be an important parameter. Okay, so this R cut. If this was too small, then it would not work at all, right? Because all of the particles would have the same spin. If it was too big, it wouldn't work either because they would all have the same spin. So there is something in between, some length scale in between, where this parameter is going to be interesting. So we don't know what that is. So what we decided to do was to calculate this spin autoparameter and then use the value of this cut that maximizes the difference between the simulations we've done. So we calculate S for each simulation, each temperature, and then we get a variance. And then we use this to, this variance to, as a function of this R cut. And then where the variance is maximum, we use that. Okay, so it's perfectly well defined. The reason you use the maximum variance, you want your phase separated and mixed systems to be as different from each other as possible. And if this is going to be giving you the input feature or your order parameter, then you want it to be different. Okay, so we did it for the Ising model too, and it's kind of interesting because this works much better than the raw spins. It's just a much better feature vector. So, when we're talking about is AI going to put you out of business, I mean, I just did that to suck people into the audience, right? It was in my abstract. Can AI put you out of business? It's not going to put me out of business, but it might put some other people out of business. So as long as you're thinking about things, all the details are taken care of, right? I mean, but this feature turns out to be important, for example. So you can see why, because it gives you just regions of non-zero compared to plus or minus ones. And so if you look at this cutoff, it matters. So in this case, the cutoff is kind of small. This is the variance as a function of the cutoff distance. It's kind of small, and here it's much larger, the cutoff. Okay, so depending on what your magnetization is, this is a simulation where the magnetization was kept constant. So the cutoff changes. So this tells you that this one parameter you have in the model has to be optimized in order to get the right physics. Okay. So what we use is this autoencoder. So you have this input data, which is that feature, which would be the affinities in this case. And you use the same thing for the output vector. Okay, they're the same. So you're not training it on anything. And then you use this neural net that reduces the dimension to 1 or 2. Okay? So this is unsupervised. All of this and all of this is input. That's your input. And your output is this latent variable here. And those latent variables are your order parameters. Okay? So this gives us the order parameters. And then if you looked at this order parameter and the variance in the order parameter, you can see that in all cases, you have a clear signature of something happening in your system at a particular temperature. Okay? And this works whether your magnetization is 0. That was a critical point. I already showed that it works for that. But this is when your magnetization is not 0. And nobody had actually looked at that before we did. So what this gives you is the full phase diagram. And these lines are, calculations from other kinds of simulations, and those do depend on system size. So these are independent of system size. So I expect that as I go to larger and larger systems, this thing will change, but this won't change nearly as much. Okay, so that's pretty good agreement. And for aficionados of critical phenomena, we have no sort of information about the critical point in the system, but we get the critical exponent correctly. Exponent beta is reproduced correctly. Okay, so then we've submitted this for publication, and the reviewer goes, "Why are you using an auto encoder? I mean, you don't have any activation functions in there, so it's completely linear. So your auto parameter is going to be just as good as your latent variable. So throw out the auto encoder and just use your affinity as your auto parameter instead." Okay, and well, it was worth a try because it's so simple, right? And he was right, or she was right. So we don't need the machine at all. The weird thing is that we would never have come up with this if we didn't do the machine learning, right? So the machine learning, that whole thing, it did teach us some physics. It taught us that this way of constructing this affinity was a good way to find an order parameter for this system. Okay, and so in fact, somewhat embarrassingly, the affinity does a better job. This is a fit to the Ising model exponent than if you use the machine learning. Okay, so you don't need the machine. You can just learn it by itself, and it does fine. Okay, so this is for a different system. The same thing, you use that peak in this to get the cutoff. And then what we found was that this cutoff distance was different depending on the composition. For low compositions, it was very strong function of the composition. And then as you went to the critical point, it became independent. Well, it became half the box length. It was independent of composition. Okay, so we argued that this was the critical region, and there you would use Ising critical exponents, and here you would use different critical exponents, mean field. Okay, so what happened? Okay, here. So this is an example of universality. So for people outside of the critical thing, this is, it's, you take different system sizes, 16,000 to 4,000. And if you plot that order parameter, they depend on what the system size is. But if you scale that order parameter by these two variables, L to the 1 over nu and L to the beta over nu, it all collapses onto one curve. Okay, so there's a collapse of the curves for all different system sizes onto one single curve. And that is a signature of universality. These exponents, nu and beta, I've used in this case the Ising universality class exponents. So these are the same for all systems. Okay? There's nothing fit here at all. It collapses all this data. That's really nice because then I can use the crossing point to identify the critical temperature in this case. Okay? The weird thing is that this also works off critical, where there is no theory for this. So except that these exponents that I use are not Ising exponents, but they're mean field exponents. Okay, so there are very, very few exponents, universality classes in statistical physics. There's Ising model that gives you most things, magnets, liquids, etc. Mean field is if you don't know your physics well enough, using mean field theory, get a different set of exponents. And there's another class of systems called what's that? I'll get to that in a bit. Systems, they're very like just 3 or 4 different sets of exponents. So there are not too many exponents to try to see what works. Okay, and so this, I'm going to sort of wrap up here because there's another talk in a bit, and so that's why people have been leaving. So this is for the Wyndham Rollinson. You got the ML works as well as the other things. Here's one for the polymer blend. And again, get good agreement with all these other methods. The black one is the one I described. All the way to the critical point, by the way. We have no critical slowing down or anything. We can just do it anywhere. And we don't even need to use the machine learning. This is for a different system, the same polymer blend, but shorter chains. That's the Ising fit. And we get good agreement with that. Simulation is a little bit off, but they were done a long time ago. They were done in like 1993. So they were very, very difficult simulations at the time. And this is for the liquid vapor coexistence curve. So there are a bunch of different systems, some asymmetric, some symmetric, and our sort of way of thinking about phase transitions using this order parameter works for all of it. So this is an argument that we could study structural transitions using a similar sort of protocol. Okay, what else? We also looked at the PEO in the ionic liquid. We don't have any other way of doing it. So this is the only game in town. So, we just basically have to believe it. We just have to believe that this is the phase diagram. It actually doesn't agree with the experiments. So I'll talk about this next week, but we argue that the experiments aren't correct in this case because they have two different papers in which they have two different phase diagrams, and neither of them looks like ours, but so it's off. Okay, so let me just conclude here. I had a whole different topic that I was going to talk about today on glass transitions, and it's a little different from the phase transitions because the feature and all that, the methods are all kind of different because you're looking at dynamics. But there's so much phenomenology involved in just introducing the glass transition. I figured I wouldn't have time to talk about it today. Okay, but I'd be happy to talk to you about it, if you're interested in glass transitions some other time. So that part, actually, when we submitted, the reviewer thought our results were stunning. And so I used that in quotes because it's not often that a PNAS reviewer thinks your results are stunning, right? Okay, so, but we have good order parameter, no critical slowing down. And so what we learned from this is the physics of how you can construct an order parameter that gives you some physical insight on why things are phase separate. Thank you.
Thank you, Arun. We can take questions now. We'll start with Gagan. So people who are leaving, there is tea and snacks. So please go have.
So if
We'll
you
join
go
in a bit.
one or two slides back, and you said yes. So the plot on the right, as you predicted, there will be a question here. So you are saying the experimental data, and then you have that model, whatever you call it, supervised stuff, right? I mean, why do you think the experiment is wrong? I mean, your model. No, I didn't understand that you say the model is correct, but the data, many of the data points are missing out, right?
Okay, so I should explain this. This interface refers to the red points are a different way of calculating the phase diagram, and that is correct. And we use that to construct a supervised model, and that supervised model is this green thing.
Right,
Okay.
but you have no data point on red data point on the middle, right? Where your model is going.
And this blue is this what I talked about today. Okay, so no data point in the middle.
No. Maybe I'll talk. So there is a supervised model you have, right?
That's this,
Which
yeah.
is missing the data on the middle, right? The blue data, whatever your result, and it only touches the red data on the two. So I'm saying that in the middle part, maybe your supervised part is not going correctly. That is all I'm thinking.
Yeah, that's what I conclude as well. Yes.
Thank you.
But it doesn't agree with the experiment either, but there's something.
Yeah, the next is.
Okay, I have multiple questions, but maybe I'll just ask the more curious one. Why did you not try out different losses? So maybe try physics informed losses or something like that?
So, so that goes into what I didn't do the calculations. So I'll have to look at what my student did in far as looking at the different loss functions. But I don't think it. So I can't answer that in a very sensible way. But I don't think it made a whole lot of difference because if you go to PyTorch, it sort of optimizes both the net and it also optimizes the loss for you. So it's very tempting to just use the default settings that it gives you. As far as the autoencoder, in the end, because it was linear, it didn't matter. We got rid of the network altogether.
And did you try maybe comparing it with some tensor network based results?
With what?
Tensor network based results, because you can do these kind of lattice simulations in tensor networks as well.
No, we did not. No, there's another method from Frank Noe's group that came out last year, which is also promising, which is a generative AI model.
Yeah.
Yeah, we haven't looked at that. No, we haven't.
You said X-ray features can help in getting the phase boundary.
The X-ray data.
X-ray data.
A14.
Okay, you can keep asking. It's a long time ago.
Like there you said from the X-ray feature, we draw the phase boundary. So like, I want to know how you have done that.
How we map this out?
Yes.
So this is an experiment. So what they did was, so what it requires is a certain weight fraction of this material. So they make it, they synthesize it, they put it in the right counter ion weight fraction, and then they look at the X-ray pattern and see what it gives. And if you look at this, so this, for example, from the positions of the peaks, you can extract the Miller indices. And based on what these indices are, this would be your BCC. Sigma gives you all these different peaks, which are characteristic of that low symmetry packing. And this is the A15, which is all these. So from knowing what the X-ray, it's sort of like any other X-ray, where if you know what your packing is, you know what the peaks are going to be. So that's how you do it. You measure the peaks, and then you see what symmetry satisfies the peak positions, and then from that you extract the phase.
Talk. Thank you for the talk. So my question is, in whatever I understood from your talk is that in the unsupervised model, so you are choosing the R-cut parameter such that from the 3D model, it can give you the correct magnetization value. So I didn't understand that why you need that auto encoder thing. Because
Right. So actually we don't need it, right? Yeah.
But earlier, so what was the logic that, so you showed a diagram, so that was the input and that there was an auto encoder and from that you got the data. So what was that part is doing that I am not.
So in that, yeah, so I presented it sequentially the way we did it, right? Because otherwise it'd be a very short talk. So but it also gives you some insight into what happens in these systems. So if you use the autoencoder as a dimensionality reduction method, so you take this large number of affinities and it gives you an auto parameter. And that auto parameter was showing signature of this phase transition. In what we later did was just take the average of the input feature, and that showed the same signature. But it's not obvious that it's going to work for everything else.
Encoder is doing different
In general. So you have large dimensionality of data, right? And then you want to reduce the dimensionality to something small. So if you had n spins at 10 temperatures, then your input feature is n multiplied by 10, that big. And then this allows you to reduce that to 2 numbers. So you can reduce the dimensionality to just 2 numbers. And that, and that can serve the purpose of an auto parameter.
Any more questions? I think we have to wind up, because you can. Why don't we go over to tea and you can continue the discussion with him. So let's thank Arun once again. Sorry, Arun, the other talk, pulled away all the audience. But yeah, please join us in the West Canyon Terrace for tea.